All right, well, today is Monday, January the, 25th? 4th? Okay. So, we just finished up and took the test over bonding. We learned about the 4 different types of substances. I don't have to in the picture. I don't have to. Okay? Ionic, metallic, covalent network, covalent molecular. How did we know if it was covalent network?
You just knew.
What were the 5?
Diamond, graphite, silicone with an oxygen nut.
All right, good. You guys knew that one.
I got that.
So on the test, which one's not?
That's the only.
You know, that's what you knew that wasn't matched up right. Okay. All right. So we've learned all about those compounds, how they bond, the difference in the types of bondings, how that bonding gives them unique characteristics, why some are solids, liquids, or gases at room temperature, why some are soluble in water, some aren't soluble in water, how an emulsifying agent, how those, link the two together, all of that stuff. But now we need to start looking at, okay, well, how do we name these compounds that we are just learned about all the bonding? Okay, so we're going to have 3 different types of, 3 different sets of rules, I should say. One for ionic compounds, one for covalent compounds, and then a special type of covalent compound called acids, where acids have their own unique naming system. So we're going to learn how to write formulas and name those 3 different types of compounds. That's our goal. Okay, so obviously you guys know this already, so I can go through this quickly. A chemical formula, it just tells me, if I say H2O, that just tells me there are 2 hydrogens and 1 oxygen. C6H12O6 in glucose, 6 carbons, 12 hydrogens, 6 oxygens. It tells me that what atoms are present, how many of each one. Okay? So in a molecular formula, though, it tells me what's present in a molecule. In a covalent molecular substance, remember, CO2, okay, it's an individual molecule, so that means I have 1 carbon, 2 oxygens, H2O. But I can also take something like this. This is a benzene ring. Is this showing? This is a benzene ring. Okay, this is an individual molecule, but the formula of it is C6H6. Notice that that's not a reduced fraction. That's what would be the, if you just like a fraction, C6H6, what would it be? CH. We would call that the empirical formula, the simplest ratio. But since molecules form definite units, we just say however many atoms they are, and it does not have to be in the simplest ratio. Okay? So it just used to represent covalent molecular substances, obviously. All right? Don't have to be the simplest ratio. So does anybody want to venture a guess what the name of this compound is?
Oh, that's easy. It's carbon 8, hydrogen 18. No.
Okay? I'll give you a clue. I'll give you a clue. You go to the gas station, you put this in your car.
Ethanol.
Well, that's 10%, the other 90%. It's gasoline, but what the actual component? Think of the C8H18.
Yes.
But like
18 bottles of gas.
You say methanol, is that correct?
I think
What letter does it start with?
Petroleum.
this is going to be octane.
Oh, we've never gotten
It's
that.
because of the 8.
Oh.
It's because of the 8. Now, I heard some of you saying methane, propane.
Petroleum.
If the carbon chain has 1 carbon, this is all my information. If the carbon has 1 carbon in the chain, it's methane. That's what natural gas is. 2 carbons in the chain is ethane. 3 is propane. That's what's in the white tanks on your grill.
Yeah.
Okay. 4 is butane, and that's the gas that's in the lighters. Is a butane. That's 4 carbons. That's C4H10. After 4, then it starts going and just using the Latin names for numbers. Pentane, hexane, heptane, octane, nonane, and then decane. Okay? So, but notice it's C8H18. The whole point is that it's not reduced. Okay? Does anyone know what that one is?
That's hard water.
Say that again.
hydrogen dioxide.
Okay, no, that's not how we would pronounce it, but, well, actually, would be the correct naming of it on an official name, but what would the common commercial name of this be?
Detergent.
I'll give you a hint. It's in brown amber bottles in most of your houses.
Mud.
Oh, peroxide.
Hydrogen peroxide. Okay? And we'll talk about what that peroxide means. Okay? Now, but notice they don't have, this is the molecule, it doesn't have to be the simplest ratio. Now, water, H2O, that's the way the molecule exists, and it's also a simplest ratio. So the molecular formula and empirical formula are the same thing. Okay? It's the simplest ratio, but at the same time, that's the way the molecule actually exists. So an empirical formula, which is what we call a formula unit, a single example of how many ions are present. It's simply a ratio, the simplest, lowest, the whole number ratio. That's what the word empirical means, by the way, for ACT. Simplest ratio. Simplest ratio. And by the way, you're supposed to be doing method test prep for science, and I'm going to give you a schedule, and we're going to have to get caught up because you're
Oh, I'm on
We're
number
like-
1, so
we're
I'm
like
doing pretty good.
7
Yeah, we're way behind, and we're going to have to catch up on that. And that could be something we work on Thursday and Friday as
Why
well.
did they just
Whoa,
randomly
whoa,
decide
whoa.
to start
We had a
requiring?
study for this.
So,
Don't.
okay, now, all right, so empirical formulas, okay? Your ions present. Now, most of the time you have your ions, you have metals form your positive ions, non-metals form your negative ions. But sometimes, and shine it up over here, sometimes we can have what's called a polyatomic ion. What's that mean?
Multiple atoms.
Multiple atoms in one ion. Okay? So you look here at chloride, Cl minus, but then you can have chlorite, and then chromate and dichromate. Those are all polyatomic ions. They're groups of atoms. They're all covalently bonded, but they have an extra 1 or 2 electrons. They're charged particle. Now, they act like a single unit. Okay? So you generally don't break them up. They're just going to treat them like a single unit, but it's going to be a group of atoms that carries a charge. I'm going to give you a sheet of these. If you're at Vestavia High School, you'd have to memorize it.
Ooh.
If you're in my class 10 years ago, you would have to memorize it. Okay, but I'm trying to get to a point to where, I'm minimizing memorization and just working you on being able to apply. However, you must be able to recognize these ions, and I'll give you that sheet tomorrow of these ions, okay? Once we go through and learn more about it. So, here are some examples just of empirical formulas. Notice it's a 1-to-1, 1-to-2. So here's a polyatomic ion. But you treat that SO4 just like you treat a Cl2. We have 3 SO4s. So you have 2 aluminums and 3 SO4s, which the SO4 is called sulfate. Okay? So polyatomic ions, groups of ions that carry a charge. We're going to have to just learn the names. We have to learn how to recognize them. Now, these are just some little tidbits for you. If a metal is attached to an OH ion, specifically that hydroxide ion, which is right there, that's what we call a base, opposite of an acid. You got acids and bases. Bases all contain hydroxide ions attached to a metal. All other ionic compounds are called salts. So any other combination of ions is going to be an ionic compound. It's going to be a general old school name is called a salt. So if you hear the term salt, it's referring to an ionic compound. But a base is a special type of ionic compound where the negative ion is OH attached to a metal. If a hydrogen is attached to a nonmetal, that's what we call an acid, and we'll look at that at the very end of this unit. Okay? Now, when we're going to write names for or formulas, we're going to have these oxidation numbers. Does anybody remember the definition of an oxidation number?
How many electrons it needs to be into
Filled up.
the gas state?
To get to noble gas. Okay, so but let's qualify that by just saying a little bit. It's the number of atoms that an atom tends to gain, lose, or share when forming a chemical bond when getting that's filled octet. Now, gaining and losing is the ionic part, right? Well, the oxidation state of sodium is +1. What does that mean?
It loses one.
It wants to lose 1. But once it loses 1, it forms an ion. So then that ion we call 1+. When the sign is afterwards, that means the electron has actually been transferred and you've made an ion. So The sign in front, so I would say the oxidation state of calcium is +2. But then when calcium bonds and it actually gains 2 electrons, the calcium ion is going to have a charge of 2+. The sign goes afterwards.
Why is everything gotta be equal?
Now listen. I'm going to show you why there's a difference here in just a second. But just relax, because this chart is 100% wrong. This chart is ions. The sign should be at the end of each one. It should be minus. You don't have to put a 1 with a minus, but it should be 2 minus. And wherever it's a 3 minus, it should be 3 minus, not -3. Okay, because they're full ions, that means the electrons have been transferred, which means the sign should go at the end. Oxidation numbers, on the other hand, the sign always goes in front. That's way more important for covalent compounds, for molecules where they're sharing electrons, than it is for ionic. Ionic, it's the same thing. Oxidation state and charge, they end up being the exact same thing, so it really doesn't matter. Because this chart's completely wrong, you can put the sign any way you want, it doesn't matter. Okay, but there is a difference between +1 and 1+. Now, let's use chlorine as an example. Get your periodic tables out, the color periodic tables out that I gave to you. LG, you got yours right there.
That's gonna be so.
Not that one, the first, that one. Look at the front. Not that one, the one I gave you first, the one that matches this one.
Wait, this one like right here?
No. The one that matches the one that's on the wall.
Oh, the laminated one?
Yeah, well, it's not, you laminated it, I didn't laminate it. Well, that means you stole my laminated one.
No, you gave it to me.
I gave it to you as a test to give back.
Oh, yeah, you stole it.
So, you're running low on this.
Oh, it's not laminated. It's not laminated.
Oh, yeah. All right, if you look at chlorine, you look at the little black numbers above the symbol of chlorine,
Yep.
and you see that it has ±1, the rest of them are all plus, 7, 5, and 3. It's got a plethora of possible oxidation states. How can that be?
Because
Okay, because we have these rules for oxidation states, okay? This last rule, number 6 down here, is something that's important. The more electronegative element is always going to have the negative oxidation state. The less electronegative element is always going to have the positive oxidation state. So, if I just have HCl, and I'm going to, well, let me do it this way. I'm going to use dots and X's. Chlorine has 7 valence electrons. So how many more does it need? 1. But when it combines with hydrogen and shares, it didn't really steal that 1 electron. It's sharing that electron. So we don't want to say that chlorine's at a -1 charge. So we use the oxidation state as -1. The electronegativity of hydrogen is 2.20, chlorine is 3.16, so this is the more electronegative element, so we give this one a -1 and this one a +1, but what that means is that chlorine has 1 of its electrons involved in bonding, hydrogen has 1 electron, it's only 1 electron involved in bonding, that X is hydrogen's electron, okay, but they're sharing, so we say its oxidation state is -1 and +1. Now if it turned completely, if it combined with a sodium, an Na, and a chlorine, that electron gets transferred, and then we end up getting an ion, which then we would say is 1-. When it's completely transferred is when the sign goes afterwards. But here it's being shared. So we just say the oxidation state is -1. 1 electron involved in bonding, and it is the more electronegative element. But chlorine can also form with oxygen. So we can have HClO. Well, again, when I do my Lewis dot structures, well, I'm going to do it this way. 1, 2, 3, 4. Okay, we can put 1 oxygen here, and remember the hydrogen's always going to be on the oxygen, right? So now how many of chlorine's electrons are involved in bonding? Still just 1, right? But at the same time now, oxygen's electronegativity is 3.44 versus 3.16. So who gets to be the negative one?
Oxygen?
The oxygen, right?
Yeah.
So oxygen has 2 electrons involved in bonding. It gets -2. The chlorine is +1, and the hydrogen is +1. Notice the sum of them adds up to 0. The sum of the oxidation numbers in a neutral compound is always 0. Okay? Now, I can figure that out without doing this whole Lewis dot structure. Because oxygen is generally -2 and hydrogen is almost always +1. So if oxygen is -2 and hydrogen is +1, and I know the sum has to add up to 0,
No,
That's
chlorine
plus
is going
one.
to be +1 as well.
chlorine has to be +1, right?
Yeah.
But all that tells me is that chlorine, it doesn't mean it lost 1 electron. That's the difference again between the charge and the oxidation state. It didn't lose that, it just has 1 electron involved in covalent bonding. It's sharing 1 electron. Well, we can also have HClO2. Now, using that same principle, what's the oxidation state of hydrogen?
Plus one.
+1. What's the oxidation state of oxygen?
+1. So oxygen is going to be -4, right?
-2, but we have 2 of them for a total of -4.
Told you don't laugh at me.
Okay?
So that means that's gonna be +3.
So that means chlorine has to be +3. Now, the back row is being real vocal here. The rest of us getting this?
What? +3? What the heck?
Oh,
It's gotta
we
be
just
zero.
ate. Okay, guys.
Okay, are we understanding what's going on here?
Yes.
Okay, we're making the sum of the oxidation numbers has to equal 0. But again, let's talk about what does that really mean? Well, oxygen is that element. Oxygen wants to bond with anything and everything that it can possibly bond with. Okay? It will do anything it can to bond. So, chlorine, we do the exact same thing with its 7 valence electrons. The oxygen, the first oxygen's here. We put the other hydrogen there. So the question is, guys, where do I put another oxygen if I have HClO2? Everything has 8. It's a filled octet. It's a happy camper. It shouldn't need any more. But oxygen has 6 electrons.
Oh, so they just connect to.
Okay.
Makes sense.
Normally they're like this. 1s2, 2s2, 2p2, but by Hund's rule in the 2p, it should look like that.
So it creates a covalent bond.
So what happens is oxygen says, hey, if we just move this electron up in here, I'll have an open spot. I can get both electrons from the chlorine, and we get this right here like this. This is what's called a coordinate, and this was in last chapter's notes. Coordinate covalent bond. That was in last unit's notes. Okay, so I'd rewrite it. Both electrons of the shared pair come from the same atom.
Where do we put this?
On the back of the paper, and use your hand write it. Coordinate covalent bond. Both of the electrons in the shared pair come from the same atom. Oxygen and then the H plus ion are the 2 main things that form these coordinate covalent bonds. But other things do, but those are the 2 most common.
You tell me, or say what
Okay.
the definition is.
Both electrons of the shared pair come from the same atom. Both electrons of the shared pair come from the same atom. Now, as you're finishing that up, it's really kind of a moot point to even define this. Because an electron is an electron is an electron. There's no difference between an electron of oxygen and an electron of chlorine. So this bond that has 1 from each is a sharing of 2 electrons between the 2 atoms. It's a single covalent bond. This is a sharing of 2 electrons between 2 atoms. It's a single covalent bond, identical in strength and character and everything. These 2 bonds are exactly the same. So that's why we could just put electrons anywhere in our Lewis dot structure, because an electron's an electron's an electron. It doesn't matter the source. But this technically is called this coordinate covalent bond. Oxygen's one of those few that can do that. So now how many of chlorine's electrons are involved in bonding? 1, 2, 3. So chlorine is in that +3 oxidation state. Meaning it's got 3 electrons involved in bonding. So if I go to HClO3, okay, HClO3, well, I just have to put another, so let's just do, what's the oxidation state going to be on chlorine on this? Well, hydrogen is +1, oxygen's always -2, so it's going to be -6, has to add up to 0, +5. Okay? Are you working something out on your calculator back there? Okay, let's put that away. So that means it has 5 electrons. Well, if I want to go and I make this, all I have to do is put another oxygen right here doing that same coordinate covalent bond. Now how many of chlorine's electrons are involved in bonding?
1, 2, 3, 4,
2, 4, 5, right? +5. That's what that +5 means. That's why chlorine can have so many different possible oxidation states. It's only when it's combining with oxygen. It's the 3rd most electronegative element. So when it combines with anything but oxygen or fluorine, it's going to be -1. There's only one way it combines with fluorine, but so it's mainly this the way it combines with oxygen and why we see the 1, 3, 5, and 7, all those different possibilities. But notice it's going in increments of 2 because of the way it's sharing its lone pair.
So then that's why you can have 7.
That's when 7 is going to be the last one, HClO4. So what's the oxidation state going to be in chlorine now?
+7.
+1, -2, -8 has to equal 0. So +7, because we put an oxygen there. So 7 is the highest possible oxidation state because that's all the valence electrons it has. So now we go and look at the oxygen family. How many valence electrons does the oxygen family have? 6. So what's its highest oxidation state? +6. So that's the biggest number above the symbol. Okay? Now the one that's bold is the most common one. That's what it tends to form. Okay? But those are other possibilities. Notice again, it goes in increments of 2 because oxygen will share a lone pair. I'm looking at sulfur. It's got plus or minus 2. It's -2 when it combines with anything else, but when it combines with oxygen, it can be +2, +4, +6. Because the way it shares the electrons, shares those lone pairs. That's what oxidation state is. Okay? So, we already kind of said this, the oxidation state of a monatomic ion, the Cl-, the oxidation state and the charge are going to be the exactly same thing. It's really going to be for covalent bonding. Okay? Oxygen's almost always -2, but when it's in a unique compound called a peroxide, it can be -1. Remember we said when we were doing Lewis dot structures, oxygen does not like to bond to itself. It doesn't bond in long chains. It always builds around, right? Well, in hydrogen peroxide, oxygen is forced to bond with itself. Okay? Whenever we have this right here, oxygen single bonded to oxygen, that's called a peroxide. And the oxygen is in the -1 state. It's an O2 with a -2, which means oxygen is -1.
Does that mean that when we're breathing oxygen, we're breathing a peroxide?
Say that again?
Like,
No, because the oxygens are not combined together.
when we breathe,
No, we breathe O2. Now, when peroxide is in a brown amber bottle, okay, it's in amber because light, and even it says cool, dark place, so light and heat both give it enough energy that it can break that bond. It does not like this bond. This is a highly unstable bond. So if you just let hydrogen peroxide sit out in the light, in a clear bottle, it's going to go to H2O and O2 gas. So if you ever see an old bottle of peroxide,
drink it.
probably see some bubbles on the side. That's the oxygen gas, and it's pretty much water.
So like you could, if you found it in a survival situation, you could drink it for one.
If it's old,
Okay.
Like how?
Oh, we
like if it's been sitting out in the sun for a year,
Oh,
Oh, okay.
easy.
Yeah.
okay? Now, if you have peroxide and you go and you pour it onto a cut or a scrape and it doesn't bubble and foam and turn white,
It's water.
it's probably pretty much just water,
And you're pouring water.
okay?
Well, then it's a waste of water to test it.
So, but peroxides are rare, but it's when the O2, so you can recognize it as peroxide. If I gave you a compound, Na2O2, well, sodium is in family 1. Sodium can only be +1. Doesn't have any other choices. And notice on sodium, there's only one number above the symbol. It's a 1. Okay? Does everybody see that? There's only one. That means it can only be +1. No options. So if sodium's +1, and you've got 2 of them,
So it's
it's
+2.
+2. So that makes this -2 because it has to equal 0. So each oxygen is going to be
Sugar 1.
-1. So that makes this sodium peroxide. Okay? But that's rare. That's a rarity. But it'll probably be on the test.
Hey, as long as it's on the study guide.
Yeah. Okay, so that's how we use oxidation number. Let's just kind of go through and practice one something else. Okay? So a pretty yellow compound is potassium chromate. If you go and you look, chromium can have a +3, +6, or +2 oxidation state. Which one is it in? You tell me. Don't say the answer out. You tell me, what's the oxidation state of chromium in potassium chromate?
I know the first
2,
one.
3, and 6.
I'm gonna go with.
Ah.
I know the first one. I know what K is, but that's it.
Okay, so you know what K is. What's K?
+2.
Well, what's the end of each individual
Oh,
one?
+1.
Each one is +1. How did you know that?
It has to be.
Well, how do you know that?
It's in family 1.
Because it's an alkali metal, and all alkali metals are +1. All alkaline and earth metals are +2. There's no other option. There's only one number above the symbol. You will always have this periodic table. There's only one number above the symbol. Group 1 are all +1. Group 2 are all +2. So if there's only one option, there's a no-brainer. That's all it can be. Okay? So potassium is +1 or a +2. What's oxygen always?
-1.
But how many do we have? So the total negative is going to be,
-8.
and what do they have to add up to?
0.
0. So it's going to be in the +6.
I was gonna say that, and then you.
Well, I know, but I wanted everybody to have a chance to work it out.
But I did it. That's all that matters.
Okay?
That's weird.
So is that one before? That was just like a weird one. That's just.
That's a unique case for oxygen, okay? And you have to figure that out from the other one. Because if you did oxygen as -2, -4, each sodium would have to be a +2, and that's not an option. All right, so one other thing along the same lines of this. A sister to this is potassium dichromate, K2Cr2O7. Same principle, +1 times 2 is +2. 7 times -2 is -14. So what's the total positive charge on chromium? +12. But how many do we have?
2.
2, so each one is. So the oxidation state is always per individual atom, not the combined total positive or negative charge. Okay? So in this one, potassium's oxidation state is +1, chromium's is +6, and oxygen's is -2. Okay? Then you multiply those by however many of those atoms you have to get the total positive and negative. Y'all with me on that?
Yeah.
Okay, because we need to be able to do that. Okay, so that's oxidation. We need to be able to understand oxidation numbers. Because those transition metals can have a variety of different oxidation numbers. 9:40, right? I only have 7 minutes left.
Yeah. Or 9, you got 9 minutes.
I don't think we're making it through this packet in 2 days.
There we are. Because this is the hardest part.
Oh, Don't cram it in 7 minutes then.
No, this whole thing is getting oxidation states and all that taken care of. Okay, so we have three types of compounds: ionic, covalent, and acids. We're going to look at ionic first, okay? And we're going to look at naming ionic compounds first. This is a life lesson. Always tend to try to be positive first.
Why?
Take the positive route first and only become negative as a last resort. Okay? Don't be like the politicians who just talk about how bad the other person is rather than saying what positive things they have to offer. Okay? So, you're going to name the cation first, and the cation is always going to be your metal. Okay? So in an ionic compound, again, remember, it's a metal and a nonmetal. A metal and some polyatomic ion. The first thing's always going to be a metal. The only polyatomic ion is ammonium. Cation. The only polyatomic positive ion is ammonium, NH4+. Okay? So, here's the only thing. If the metal is a transition metal with more than one possible oxidation state, we have to use a Roman numeral to tell what state it's in. And I'll give you some examples of that. Then we're just going to name the anion, the negative ion last. That's going to be your polyatomic ion. Now, ions always end in one of three suffixes. If it's just monatomic, no other elements are present, it's going to end in I. Cl is chlorine, Cl minus is chloride. O is oxygen, O2 minus is oxide. N3 minus, nitride. So if it's just by itself, it's going to end in I. If there's oxygen with it, it's going to end in either ite or ate. What can you see is the relationship between the ites and the ates? What's the only difference between sulfite and sulfate?
It's between the four.
There's one more oxygen.
One more oxygen. Notice the 8 always has one more oxygen. The charge is always the same. Okay? Just one less oxygen. Now, the problem is that the 8 does not tell you what the actual charge is going to be or how many oxygens there are. Okay? Because NO3 is an 8, SO4 is an 8. You just have to know the 8s. But the ite will always be one less. Until you get down here. So again, we have the 4 different ways in which chlorine and oxygen can combine. Okay? So they named this one chlorate. So the one with one less oxygen, chlorite. But they only have 2 suffixes, but they have 4 ions. So we had to come up with some prefixes. Well, what's a prefix for over, an overactive child? Hyper. So but they take the high off and they just call it perchlorate, but that comes from hyper, chlorate. So what's the prefix for below? Hypo. Hypodermic needle is below the skin. Hypoglycemia is too low blood sugar. But for some reason, they don't take the high off of that one, and they keep it as hypo.
See, these chemists, they need to...
Okay. Well, I think they were just not didn't want to make chloride feel bad and think, oh, pull chloride, and so they kept the high on there for hypochlorite.
They just have too much time.
Yeah.
He's not.
Okay. Hypochlorite. But now listen, look. What do we know about elements in the same family? Shine over here again.
Same property.
The same property. So if ClO3 is chlorate with a -1, what's BrO3 going to be? Bromate. Besides the miracle, what is IO3 going to be? If this is bromate, chlorate, iodate. That's why it would be a miracle. Iodate.
I don't get it.
No, it's like I date. It's a miracle.
Yeah. Okay. So notice they would all have a -1. So if I know ClO3 is chlorate, using these rules, I can figure out everything else. ClO2 is chlorite, ClO is hypochlorite, ClO4 is perchlorate. BrO3 is bromate, therefore BrO2 is bromite, BrO is hypobromite, BrO4 is perbromate. They all to be the same. So if sulfate is SO4, 2 minus, what's SO3 going to be? So what's SeO4, 2 minus going to be? No, so Se is selenate, and SeO3, selenite. And they're all going to be minus 2. These are all minus 1, all minus 2, and these are all going to be minus 3. So phosphate and arsenate are going to be the exact same thing. So the reality is the families are all going to be the same. The only ones that are different are your carbonates and your nitrates. These two are unique. They don't fit the trend. Okay? Two others that are polyatomic, you just have to memorize, just know, cyanide and hydroxide. Cyanide and hydroxide end in I, but they're not monatomic. Just two unique ones. All right, so let's finish in the last 2 minutes. Look at some examples. Okay? So I'm always going to have a positive thing and a negative thing. So the positive thing is almost always just the name of the element. You don't put any suffix or anything on it, just sodium. And then since there's no oxygen, it's a monatomic, it's just chloride. So what's this one going to be?
Calcium.
Calcium.
Potassium dichloride.
Now you don't need to have any kind of prefixes or anything, nothing on that. You're just going to name the ion. No, you don't have to tell how many. Calcium's +2, fluorine's -1. There's only one way it can combine. Okay, so you're just going to say fluoride. Now notice the spelling of fluoride. It's UO. If you go OU, it's flour. It's fluoride. Okay, now notice here we have a polyatomic ion. So you still just name. Notice we don't have to worry about the 3's and the 2's. It's just calcium phosphate. This is phosphate.
Why do you not use calcium fluoride?
Because there's no oxygen. Ites and eights all have oxygen with them. If it's monatomic, just a single atom, the only one type of atom present. There's just 2 fluoride ions present. But, okay, I don't think no, I don't. This is where we'll pick up here tomorrow. Pick up here tomorrow, and then I'll be able to finish this. I'll probably be able to finish the whole unit tomorrow.